Hello, my name is Joseph Landolph, and my project is going to discuss the applications of linear algebra in cryptography. Bit of a disclaimer, cryptology has nothing to do with my major, which is actuarial science. Cryptology just interests me, and I also had a hard time finding a decent application of linear algebra due to actuarial science's more statistical nature. Cryptology is an art form that dates back to the beginning of civilization. Ever since people could communicate with one another, there were certain things some people did not want other people to know. They would hide their messages through patterns in their words, or represent letters with symbols. This is the basic form of cryptography. It involves creating, encrypting, and solving different codes to intercept messages not necessarily meant for them. Cryptography still has many uses today, with so much private information being stored on the internet. To secure their data, many people use software to encrypt their data, so prying eyes will not know what they're looking at. This is a big aspect of daily life, as well as in war. One type of code, which is extremely difficult to break, makes use of a very large matrix to encode a message. The receiver of the message decodes it using the inverse of the matrix. The first matrix is called the encoding matrix, and its inverse is called the decoding matrix. For my example, I'm going to use a small 3x3 matrix just for simplicity's sake, but much larger matrices are typically used for this type of code. The bigger, the harder it is to unencrypt. First, we need to figure out what the message we want to send is. Here, we can just have our message be meet tomorrow at midnight, a real creepy message to somebody that doesn't know what it is. Next, we will set our encoding matrix and also our decoding matrix. The recipient will need to know at least one of these matrices, so they can find the inverse by row reducing whichever matrix you tell them, augmented with the identity matrix to find the other matrix, to either read or send out more messages. Here are the matrices we will use for our example. Now, we will assign each letter of the alphabet a number in order. For example, A would be equal to 1, B would be equal to 2, and so on. A space or a break will be assigned the number 27 because there's only 26 letters in the alphabet. Now, we translate our message into these numbers, as you see below. Now that we have our translated code, we need to put these numbers into vectors. Since we are using a 3x3 matrix, we break the enumerated message above into a sequence of 3x1 vectors like so. Note that it was necessary to add 2 spaces or 27s at the end of the message to complete the last vector. We now encode the matrix by multiplying each of the above vectors by the encoding matrix. This can be done by writing the above vectors as columns of a matrix, and then perform matrix multiplication of that matrix with the encoding matrix like so. The columns of this matrix give the encoded message. The message is then transmitted in the following linear form. To decode the message, the receiver writes this string as a sequence of 3x1 column matrices and repeats the technique using the inverse of the encoding matrix. Thus, to decode the message, they will perform the matrix multiplication and receive a matrix that should look familiar to you. The columns of this matrix, written in a linear form, give the original message. And now, you can meet in secret with confidence that no outsiders to your conversation will ever be aware.